Greetings, it's Paul Bamberg with the introductory video for Class 10 of Math 117, in which I propose to introduce you to the concept of the Lebesgue integral as used for calculating the expectation of a random variable. Last time we dealt with simple random variables that could take on only values in a finite set. Now we're going to be a little bit more daring and extend our treatment to positive bounded random variables. Positive means the value can't be negative, and bounded means there's some positive upper limit on it. Of course, we're going to start out with the usual probability space, and now we are going to partition the image of x and take advantage of the boundedness to partition the image of the random variable x into a finite number of disjoint intervals. In order to make them disjoint while their union is the entire image, what we're going to do is make each of these intervals closed at the lower end open up the upper end. So there's no overlap and no gaps. We do this in two steps. First, since the value of the random variable can never exceed m, what we will do is break up the image into m pieces, the first one extending from 0 to 1, the next one extending from 1 to 2, and so on, with the last one extended from n minus 1 to m. Then we'll pick a little n and divide each of these unit intervals into 2 to the n equal subintervals. For each value of n, we get a different partition, with the partitions becoming finer and finer as n becomes larger and larger. It'll take you a while to get used to Deneen's notation for one of these. It is I super n j comma k. The n means we have divided each unit interval into 2 to the n parts. The k specifies which unit interval we're in. We're in the interval that runs from k to k plus 1, and j specifies which of the 2 to the n subdivisions we're in. We're in the subdivision that goes from k plus j over 2 to the n up to k plus j over 1 plus 2 to the n. So these partition the image of x. And if x just happened to be constant on every partition, we'd have a simple random variable, and we'd be back to the previous case. But we're not assuming that x is constant on every partition. Instead, we're going to make that be the case. But first, let me talk about why we're partitioning the codomain. You might say, I've studied Riemann integrals. Why don't we just partition the domain? And here's why. You can partition the domain as finely as you like and still have an enormous variation of function values within each subinterval. If you think, for example, of the notorious function that equals 1 for rational x and 0 for irrational x, then no matter how fine a subdivision you make, you've always got points in the subdivision where the values 0 and the values 1 both occur, and for that reason this function doesn't have a Riemann integral. If we partition the codomain, this can't happen. Within one of the sets in our partition, the largest and smallest values of the random variable differ by 1 over 2 to the n, the size of a partition. Now, each of these intervals in our partition is a Borel set, and because x is a measurable function, the inverse image of that Borel set must be in the sigma field generated by f. If you think about concrete examples, you realize this could still be very messy. A perfectly reasonable sample space would be the space of all possible outcomes of the superpole, and the random variable x might specify the location of the football after the opening kickoff. Then one of the sets in the partition will be I super 1. That means we've broken each unit interval into two pieces, and we're interested in the one that starts at 25 and goes from 0 over 2 to 1 over 2. In other words, the inverse image of that is the subset of all Super Bowl outcomes with the property that after the opening kickoff, the ball is located between 25 and 25.5 yards from the goal line. In spite of the fact that the sample space is more or less impossible to describe completely, if you know the probability distribution for runbacks of the opening kickoff, you can calculate the probability of the event that the value of x lies in that partition. Now let's try to turn x into a simple random variable, one that's not only simple but positive to boot. All we have to do is to round down the value of x on each interval in our partition to the value at the lower endpoint. So what we do is, having chosen n for all values of k and for all values of j, we take k plus j over 2 to the n, that's the value at the lower limit, and multiply that by the indicator function of that set. We now have a random variable that assumes only a finite number of values. Of course, we'll get a different random variable for each n, so we've constructed a sequence of random variables, and Deneen calls that the canonical sequence. Here's a list of the properties. You might have to stop the video and think about a couple of these for a minute, but they all are fairly obvious. The difference on any point in the sample space between x sub n and n cannot exceed the maximum amount by which you round down, namely 1 over 2 to the n. Because we round down less when we're using a larger value of n, this sequence of random variables for any particular point in the sample space is an increasing sequence of real numbers. That is, we've got an increasing sequence of random variables. X sub n always lies in between 0 and x, and furthermore, the expectation of x sub n can differ by the expectation of x sub n plus 1 by at most the amount that you change things by when you do the smaller amount of round down indicated by x plus 1. Turns out this is guaranteed to be less than 1 over 2 to the n plus 1. These expectations are positive numbers. They form a convergent sequence, and it's possible to prove, in the very special case where x is a simple random variable, that this sequence of positive numbers converges to the expectation of x, which we already knew how to calculate. But what if x is not a random variable, a simple random variable? Then we have to use this as a definition, and we say, in order to compute the expectation of a simple random variable, we're going to construct this canonical sequence, evaluate the expectation for each of these simple random variables, and then take the limit as n approaches infinity. Once we do this, it's fairly easy to prove, and you may get some practice with this in class, that the difference between the expectation of x and the approximation expectation of x sub n is bounded by 1 over 2 to the n, which is going to guarantee that as n approaches infinity, it approaches 0. Furthermore, we can extend that increasing sequence theorem that we considered last time to the case of positive bounded random variables. That is, we can now prove if x sub n has the same limit as y sub n for any point in the sample space, then, as you might well have guessed, the limit of the expectation of the sequence x sub n is equal to the corresponding limit for y sub n. And the proof proceeds exactly as it did last time. That's the advantage of this approach. It doesn't get more complicated when we consider more complicated sorts of random variables. Now I can explain formally what we mean by a Lebesgue integral. Here's our formula for the expectation of a bounded positive random variable. It's the limit of the expectation of certain simple random variables given by a formula which you have seen before and will see again. And we can use the usual representative point idea. That is, for each subinterval in the partition, we choose a point in the sample space, let's call it omega j comma k, to go along with the set in the partition that has subscripts j and k. And what makes the point a representative point is that if I evaluate x on it, I get a value that I will call x j comma k. If I use this specific value, x j comma k, instead of the value k plus j over 2 to the n at the lower point in the interval, I'm not going to change the expectation by much. I'll change it at most by 1 over 2 to the n. So in the limit, it makes no difference which I use. And in doing this, we've now defined the Lebesgue integral. So here's our definition of the Lebesgue integral of a random variable x. We take the nth term in the canonical sequence. We take the value of x at our representative point, and we multiply that by the probability of the inverse image of that partition, sum over everything in sight, and take the limit as n approaches infinity. But we can rewrite this solely in terms of the real numbers, the same sort of sum, except x applied to the representative point is the value x j comma k, and the probability of the inverse image of the interval is exactly what we mean by the probability of the inverse image generated by random variable x. So this is a definition of Lebesgue integration that makes no reference to the sample space. It refers only to the real numbers. You can in fact define Lebesgue integrals without ever mentioning probability, but Deneen's approach, in my opinion, is ingenious. We all have a good intuitive sense, I feel, of what's meant by a probability measure. We don't have that same intuitive sense for an abstract measure, so this approach to this difficult topic is the way to go. What properties does this Lebesgue integral have? Well, they have properties that you would like, and it turns out most of them are fairly easy to prove. Since we've got a positive random variable, the expectation can't be negative. As is the case with integrals in general, the expectation of the sum is the sum of the expectations. If one random variable is always larger than another, so is its expectation. If the random variable cannot have a value in excess of m, and here the absolute value sign is superfluous because we're considering only positive random variables, then the expectation cannot exceed the maximum possible value. And finally, if you've got a set where, as long as you consider only points in the sample space that lie within the subset A, that correspond to the event A, then if you take the random variable and multiply it by the indicator function for the event A, the expectation cannot exceed m multiplied by the probability of A. These are easy to prove, and you'll get some practice in doing so, but it might be worth stopping the video now and just thinking about these to convince yourself that none of them is any surprise. Well, what are we going to do next? You might already have guessed this. We're going to remove the boundedness restriction. And once we remove the boundedness restriction, we're going to put it back in by defining a new bounded random variable for each value, each integer value m, where we're going to truncate the value of the random variable. Basically saying, if according to the formula, the payoff would turn out to be greater than m for some point in the sample space, we'll cut it back to just equaling m. So we're truncating the values of the random variables. Having done this for each m, we've got a positive bounded random variable. We can calculate its expectation, and assuming that the sequence that results has a finite limit, we just define the expectation of the positive random variable x to be the limit, as m approaches infinity, of the positive bounded random variables where we've truncated the values at integer m. When we do this, we can prove that if we have any sequence of random variables converging to a limit n, the limit of the expectation equals the expectation of the limit. Again, the expectation of a sum will be equal to the sum of the expectations. And finally, if we've got an integral random variable x and a random variable y that's always in between 0 and x, then y and x minus y are also both going to be integrable, and furthermore, the expectation of y cannot exceed the expectation of x, and the expectation of x minus y, that's a perfectly good random variable now, is equal to the difference of the expectations. Now let's think about how we might actually evaluate these things, because we're now talking about some rather messy sums, and nobody likes to do sums. People would much rather do integrals. There's a special case in which we can reduce the problem to integration. Let's denote by p sub capital X of x the probability that the random variable x that has a value that lies in the Borel set from 0 to x. Now, my favorite example of this is for the random variable, you send someone off to the grocery store and ask them to buy a package of hand-cut cheese. When cheese is cut by hand, the weight of the package can be any positive real number within reason, up to a couple of pounds, let's say. And therefore, this probability is not only an increasing function of the upper limit little x, it's a differentiable function of it. In that case, you can calculate the probability that x lies in some short interval. What's the probability that your randomly chosen package of cheese will weigh somewhere between 0.67 and 0.68 pounds? And you can approximate that probability by the derivative of the function p times the width of the interval. And when you sum this over x, you can approximate the result as an integral. You just replace the delta x by dx. So you can calculate the expectation of x as an integral. You say, aha, I knew you were going to get back to doing Riemann integrals. But not exactly. This is not an integral over the sample space. It's not an integral over the domain. It's an integral over the codomain of x. So we're not trying to integrate over a sample space consisting of packages of cheese. We are instead doing an integral over the codomain over the weights of those packages of cheese. You will see numerous examples, because they're about the only ones where we can do, where we will therefore be evaluating these Lebesgue integrals by doing ordinary Riemann integrals, but they'll be Riemann integrals in the codomain. Well, yet again, almost precisely 20 minutes, and I am done.